Okay. Fortunately, I won't sound too extreme or crazy after that. No offense. I want to talk about how to potentially do planetary missions without a lot of the headache that telecommunications across the solar system involves. And the idea actually was alluded to in an earlier talk today, the tether spacecraft asteroid fleet thing. But I just want to emphasize how much of an advantage doing things right can save you. So I'll say a little bit about why it's so hard to actually do a planetary mission and get reasonable downlink of data. Describe what I'm going to call a more physical solution. Well, first of all, I'll use a CubeSat asteroid encounter as an example of the problem and an example of how the approach I'm going to suggest would make it a lot easier, and then do something that's going to sound really, really crazy, but that's all right. Since I'm using Marco and Iris 2 as an example, and a lot of previous presentations here have also mentioned that they were baselining that, I just thought I'd do a slide on what that amounts to. The system allows varying data rates from as low as 62.5 bits per second up to 256 kilobits per second. It's 35 watts of input power, and although the transponder itself isn't too large, when you add in the antenna and the power systems that are required to run it, it actually takes up something like 2U out of the 6U spacecraft. And that gives you 8 kilobits per second of downlink from Mars. So the question is, if you had something like that at 3 AU doing an asteroid flyby, what would you get back? And, well, first of all, you've got a problem that at 3 AU, solar power, the solar arrays are only going to give you about 44 watts per square meter. And that means the idea that you would actually be able to power that 35 watt transponder is pretty much not going to happen, not directly. You're probably going to have to resort to something like batteries, running the downlink off batteries, and charging between downlinks. Now, for an 8-hour downlink, that's actually 280 watt hours, which is quite a bit for a CubeSat. Unfortunately, the way the DSN works, there's overhead and communication, calibration time associated with every track they support. So if you ask them for a 1-hour track, you're asking them for 2 hours of antenna time. They don't like that. So shortening the downlinks isn't going to help. I think that's something you just have to deal with. That approach would get the power down to a reasonable level, but even so, given the range to Earth, 2 to 4 AU, you're looking at 250 to 1,000 bits per second. And that means at most, for a modest monochrome image, 1 megapixel, 16-bit depth, and fair compression, you're looking at over an hour to downlink one image. One image, I realized my view graphs were all words and I had to put in some pictures, so this is the kind of images we're talking about. Now, the problem with the Deep Space Network is, you could say, give me enough tracks, 1 image per hour. Hey, New Horizons did that for 6 months and nobody complained. People actually did complain. But the fact is, they only have a finite number of antennas. The configuration they're currently building towards is 12, 34 meters, decommissioning the 70s. And that's got to support a whole lot of spacecraft. And I hate to say it, but CubeSats are not going to be their highest priority, because they're going to have missions at Mars sending down a megabit per second. And anyone looking at that is going to say a spacecraft that's sending down 0.1% the data rate is not making an efficient use of that antenna time. So on top of that, if the whole idea of planetary CubeSats works well, then there are going to be a whole lot of them out there. which means realistically you shouldn't be counting on more than maybe one track every week or two. Which means that one image per hour, you've got a problem. Now, what occurred to me is that actually data storage is a lot easier in this kind of environment than sending the data. What made me realize this was having to buy a memory stick and realizing that I bought a terabit of memory storage for about €40. And actually the mass and volume of that package, the only reason they're as big as they are, just a typical memory stick, is so you don't lose them. Now that's not a fair comparison, they aren't flight rated, but the point is you can get a lot, relatively speaking, of mass memory on a spacecraft compared to what you can send down. What you probably are talking about needing, well, Cassini on a satellite encounter did about 4 gigabits of recorded data. New Horizons was 64. 250 of those images I was talking about, this time in 5 filters, 5 gigabits. That's the range of data volume you're probably talking about. Though, of course, that depends on the number of instruments, what exactly you're doing, but as a ballpark figure, that's what I'm talking about. So my idea is, why not just bring the data home? If you flew a mission with 1 by 3.15 AU orbit, do an encounter at apoapsis, the 3.15 is there for a reason. Do the whole encounter at a very low data rate where you're just making sure everything's working, send down a few highly compressed thumbnails, you know, something like 2 images a week or something. Then after the encounter, you're on an orbit with a 3-year period exactly. So that means in another 1.5 years, you come back to perihelion and back to Earth. It doesn't have to be a flyby. It doesn't have to be any sophisticated navigation. If you get within 1/10 of an AU, you're in great shape. Because, well, you're at 1 AU, so you've got plenty of power to transmit. Though you probably still would want to rely on batteries. At that power, at that range, inside of 0.15 AU, an IRIS transponder is maxed out at its peak 256 kilobit per second. That means you're sending down one image every 17 seconds instead of 70 minutes. And that means, you know, you can return a good, sizable encounter data set in just a few weeks, just a few tracks, and probably a few weeks if you aren't going to stress scheduling with DSM. And this is just what the data rates look like as a function of time from launch. The encounter is in the middle, and the Earth encounter where you're downlinking is at the right, and that's a log scale, so you're talking about a factor of 1,000 improvement. You just have to be patient and wait for a 1.5 years. Now, this is all very hand-wavy. This is not a mission concept. This is just an example or an illustration. You wouldn't want to do it exactly this way. There's some risk involved by increasing the required duration of the mission. There are games you have to really play with balancing the telecom, the antenna size. Could you make it smaller and squeeze in another instrument, blah, blah, blah. Operationally, I don't know if 1,000 bits per second once every 2 weeks is enough to safely operate the spacecraft through an encounter. You might want to do something about that. And one thing that would help is if you had a transponder that had a low power mode. As far as I can tell, IRIS does not currently have one. So you're stuck with that 35 watt input power. And I'll just mention that you can do this with any mean motion resonance. If you only want to go out to 2.17 AU, it's a 2-year instead of 3-year resonance before you go back to perihelion. You can go out to 4 and do a 4-year mission. So I'm going to go to the crazy part. If you had a whole lot of data, I mean a really, really large data volume, why not just literally send it home? This was actually done in a series of American reconnaissance satellites. the Corona program from 1959 to 72, where they actually recorded satellite imaging on film and used a re-entry capsule to drop it back. You wouldn't have to have the airplane catch it in the air because you don't have to worry about the Russians coming along and snatching your spy satellite data on the ground. You might have to worry about a farmer deciding he wanted a souvenir, but anyway. So the question is, how small can you really make a re-entry capsule? Could you fit one into 1U, half a U? Something you could fit in your pocket? And how much mass memory could you squeeze into it? This is a planetary CubeSat mission, and I'll have to say, I don't think the kind of data volumes that would justify this are really something a planetary mission needs to face. But there are some applications, very high rate, short duration magnetospheric missions, where this might actually be applicable. And people are, talking about CubeSat-sized reentry vehicles. One of the PSDS-3 studies that just finished up was for a Uranus entry probe that was CubeSat-sized, a little bit on the heavy side, but the question is, could you scale that down to a lower entry velocity, a tenth the size, and put a couple of terabytes of mass memory on it? So just conclusions. Really, instead of fighting the difficulties of transmitting data from multi-AU distances, particularly when you're farther from the sun and have low power, I think it's better if there's any way to orchestrate the mission to just get back to Earth in a year or two, and a resonant orbit gives you a free return. It's better to wait, and when you're close, do the data dump. And if it's really extreme, I would really like to see if the re-entry capsule would work. And that's all I have to say. Okay.
Coming from a round-trip background, I would maybe suggest, instead of trying to fit a round-trip capsule inside a 1U, trying more to increase the cross-section, by like a light deployable, to reduce the basic coefficients and to have something more efficient.
Okay, that makes sense.
Thank you. I'm afraid I can't remember the university, but the university in Germany with the Merkur 2 re-entry capsule, which is, I think, roughly a half to three-quarter U re-entry system from here. And they're demonstrating it with colleagues from Cape Town. I think it was supposed to have happened already, but I can give you the reference. Someone's built this with the latest.
I would definitely like to see those references.
Or Stuttgart, maybe.
It's Stuttgart.
Japan also. The main event in the
Yeah.
6 unit CubeSat have one landed.
No, but this was a re-entry from Leo capsule. I've actually, I've built one. I've seen one.
Excellent.
Yeah, it's continue there.
Hi, so do you have any wise suggestion for Mars? Because what we were talking about is mainly for asteroids, and basically for Mars would be like a sample return.
Yeah, the real problem with this is it only works for a flyby. If you have to propulsively get from Mars orbit back home, my recommendation for any planetary orbiter is actually having a relay satellite. Because you're probably going to want to support multiple CubeSats at Mars, and them all funneling through one larger relay is probably the best way to go. It's not a new idea. Just need somebody to build the relay satellite.
Yeah, I agree.
Thanks for the presentation. I found it a bit unreasonable to having Iris radio just for transmitting data near Earth. I mean, you don't need that fancy thing near Earth's proximity just to download your couple of gigabytes of data. I mean, you can go with much simpler design, some patch antenna, some, I don't know, with that sort of thing. It should be possible, and then timing of this less fancy or few watts consumption communication to downlink the data.
Well,
This is not
I agree Iris would be overkill, but you do also want to have some downlink during the encounter, unless you want to trust completely on spacecraft autonomy. And also, if you don't want the difficulties of navigating to a close Earth encounter, I don't think a patch antenna would do. I was saying if you even get within 1/10 of an AU, this would work. If you want to restrict that and say closer than lunar distance and you have to navigate that, then yeah, a much simpler system would work. I was more illustrating the basic principle than doing a specific use this hardware suggestion.
Any further questions?